doubts, from limitations, power to discover the roads untraveled and unlock the potential you didn't know existed. Until now. The Lenovo ThinkStation P10, co-designed with Aston Martin, masters of iconic design and performance engineering, featuring a breakthrough dual-processor platform, superior graphics support to handle the most extreme workloads, the epitome of form and function, with an innovative modular design and unrivaled accessibility. With an advanced thermal architecture to push out maximum component performance. Optimized for both desktops and data centers to run complex workflows seamlessly. Expand your realm of possibility. Because at this elite level of performance, your brilliance will be truly tested. What will your legacy be?
So, don't worry, I'm not going to put a product presentation here with my slides, but you are very welcome to visit us, of course, below on the booth and speak with us about the possibilities we have. And you saw it already, the ThinkStations have been designed actually by Aston Martin. But that's all I'm going to talk about the products. Based on the conversations that I have on a regular basis within the automotive industry, we see that in today's automotive design environments, time to market pressures are intensifying. And also technologies like AI and virtual reality are accelerating. At the same time, it's critical for those industries to avoid complex IT setups, having the wrong hardware, and of course, scalability issues, but also to having the wrong partner aside. We from Lenovo have partnered with Autodesk and also with NVIDIA, industry specialists who have a deep understanding of sector-specific needs. And together, actually, we built a magnificent tree in order to support you with your challenges or those industry-specific challenges. So with the right partner and the right persons that can help you and support you, and also the right hardware on your side, nothing is impossible. With these words, I hand it over to Pascal, who will definitely show you what is possible with our ThinkStations. Thank you very much.
Thank you.
Yeah.
Great.
Thank you.
Thank you. Okay. Actually, let's start with the safe harbor, because I have to, because we will show something that is not in the release yet at the later point. So just want to make sure you are aware that this is, we are showing a tech preview. It might come, it might not come, it's likely coming, but do not make any buying decisions on what you see today. Where there is light, there is also shadow. What I mean by that, actually, is that when going into that topic, light simulation or optics at all, you are prompted with some of those terms that are unfamiliar, but you need a clear understanding what they are. So, sorry, words like acoustics, dispersions, wavelengths, Kelvin, luminance, candela, scatter coefficient, photometric parameters, all these kind of things you get prompted in your workflow is something you should have at least an understanding or read some books or Wikipedia entries, etc., to get familiar. Because sooner or later in the software itself or in your use case, you are prompted with those kind of things. And this can sometimes be a tough topic, right? Especially for those who don't have a strong physics background. What I get often asked is VRED an accurate renderer, right? And how do you measure accuracy, actually? It's a good point, because rendering in general is an approximation of the real world. And I think those algorithms are not not a secret anymore. So I think how the applications differentiate from each other is simply on how they approximate things. A little bit, I think, on the features they offer. One application has Spectral, some other application does not have Spectral, but it's important for certain use cases. And the kind of values you can input in the application. So when getting values, physical values, those kind of things, luminance or dispersion, or all those weird things maybe in the beginning, you need a place to type in that, right? Otherwise, it doesn't matter how accurate or how less approximate a renderer is actually. I found that a good example. You see that's really real time, and it just shows that you don't need any Photoshop to flip images in the future. What does that mean in terms of color? Color is essentially the reflection of light, right? And light travels in wavelengths, so that's the first thing to understand. And one wavelength hit another wavelength or another spectrum, collects the spectrum, and is reflected in another wavelength. And sometimes even wavelengths affecting each other, that they absorb color, not just adding information like in that example, right? If you in a spectral environment and the white light wavelength hits the green one and then afterwards the red one, the wavelengths that get through those two classes is what we experience as orange or yellow, basically. And that's, I think it's called subtractive color mixing, something like that in that example. And that is really, really important, because without spectral rendering and the possibility to render in wavelengths, it's kind of inaccurate already from the very beginning. And then also, in this context, it's important to understand a little bit the color management you are using or dealing with inside the application. Because when doing light simulation, you often render and work with values that are outside of the range that can be displayed. And sometimes they are even outside of what can be perceived from us as a human being. Right? In reality, when you look into such a tail light of a car, you just see red. And if it's too bright, then you maybe feel some pain in your eye, but you would never ever see something like that orange, white, reddish fade inside the tail lamp, for example. But as you can see, it helps to understand or perceive intensity or light as light for us. There's a maybe more a physiological effect, but more close to the eye or what we perceive as a human being would actually be that example, the red one. But we cannot feel or see in super bright intensities on the screen. Otherwise, I think OEMs would simply build in screens that are bright enough instead of having tail lamps driven by LEDs. So it's important to understand that it often requires a tone mapping to get from those super large ranges of colors and intensities down to something that can be displayed in sRGB as well, which is usually the tone mapping. And VRED offers various or different tone mappers that can help with that. VRED has even some tone mappers that give you the possibility to have a kind of analytic view on those simulation data with a luminance and illuminance tone mapping, for example. In that case, I took an example that is maybe easier to understand in the first place because we are prompted with that in our everyday life. So what you see here is a factory or a grocery store actually with different lighting, and it is very important when doing those bigger projects or malls or whatever, where you have hundreds, thousands of different ceiling lights, spotlights, etc., how they work together. What is the overall illuminance or intensity or light or color temperature they produce in such a big scenario? Not just that it's important how products are lightened. It is also important if you think about if that's a factory or workspace, it is also important in our work environment, how much light we have, what color do we have, where do we feel comfortable, right? How much daylight is there and how much, in addition, artificial light is needed to feel well in a work environment. Another example where light simulation in VRED in an early stage or later stage totally makes sense if we want to see, or where we want to see the effect of geometry working together with light. So in that bit older example, we really have two LEDs that go through that optical light guide and come together at the corner, and it's important to see or understand in a very early process what happens there. Right? Are there any unwanted effects there? Is that okay from a designer's point of view? What really happens there? And doing that without having a physical prototype in an early stage, at least seeing the direction is pretty cool, right? Also, light leaks is a very important topic. Is my geometry close or perfect enough that there's no light leaking into areas where I don't want to have it? Just from a let's say engineering, but even from a designer's point of view. Another great example is where light simulation helps to make decisions or can help engineers and designers to work together is in the decision-making and solution-finding process, actually. That's a quite old example I did many years ago. I was reverse engineering that from my dad's car, actually, if it's familiar to you, but it's not customer data, but it shows quite good the effect. The first one is where we have that closed shape is actually something the designer wanted. That clean look, especially not at night and in a day design is what is wanted. The effect when you emit light into that, you can see underneath. So what happens here is if there's an LED bringing light from the down into it, it basically reflects straight back to that. That means the light does not distribute homogeneously inside the ring because it's just reflected back. But it looks good. The second example is, or the example in the middle is probably what the engineer would suggest to do, right? Because light is, you can bend it. No? You can have a different shape and then the light would split and go to the left and the right and would guarantee that it distributes or reflects actually very homogeneous to the left and the right and comes together at the top ring, but it doesn't look sexy. So the solution might be what we have at the very end is a compromise where we have the outer shape and introduce the kind of triangle prism into the center to bend the light, but from the outside, especially when not lighting up in the cold design, it looks what the designer wanted. And to have the possibility to do that and play around with geometry, and maybe you have seen the earlier session where we live connect areas into VRED now, running in full GI ray tracing and do those kind of things while manipulating the geometry at the same time, could be a very interesting and efficient use case or process in the future by designing things. What different approaches does VRED offer to do that? So you might have heard about path tracing, photon mapping quite a lot, and different use cases require different approaches sometimes. There's the one use case where we want to basically look into something. By the way, all renderings created here are done with VRED, so there's no imagery or photographs in it. But the first use case is look into the light. And what we see here is basically the reflection of the emitting light source, which is usually an LED, but it bounced millions, 100,000 times inside the geometry, reflecting, refracting, scattering inside the geometry. But at the very, very end, we just look into the from the LED source itself. For that use case, path tracing is totally enough and probably the fastest approach. But VRED also has a photon mapping, which might come in handy or better when using those kind of use cases, right? You have an emitting light source that goes through an object and class, whatever, is refracted, because what we see then later on the wall or on the street is just caustics. And we want to see how that looks like when the light is arriving the wall or the street. The challenging part on here is that the ray tracer does not see the light source itself. So it needs a lot of samples and rays to send around to then finally hit back from the wall and find that light source, which is on the right side where it can trace against. So in photon mapping, it's an option you can turn off switch to in the render settings. Has a different approach, a two-step approach basically. It first sends out light or values from the emitting light source into the scene and captures that in a map, in a photon map basically, right? That's the first pass. So you get a lot of information in the different areas what intensity or what values are stored in there. And in the second step, the camera looks into the scene or into the image and evaluates the light map and the values that have arrived from the first step, basically. So if you want to see how it looks when the light distributes outside the lamp, which is basically caustics. Whenever caustics come in play, then photon mapping is a better approach to do so. In addition, VRED also offers different, as I said, different analytic tone mappings, because it is nice to look at something like we see on the left. But what does that really mean, right? There's tone mapping involved, there's my screen, and I can't judge if that is bright or not so bright. I can see just the relations inside the image, but I don't have any information if that is too bright or not, or if it got tone mapped. So VRED also has an illuminance tone mapper, which gives me at least a hint or the information where are the bright areas by the light that is receiving. And we also have a luminance tone mapper, which takes in account which material or which color is assigned. So that's what you see on the very right. And it looks like that the chance for the white bunny rabbit is is higher to survive when hit by a car, because I can see it earlier. The white reflects much better than black. It's something we know, but that is an analytic view on what we all know already. What other features does VRED offer for light simulation? So, of course, we need photometric parameter. That's a setting in the render settings that switches basically your UI from meaningless intensity values to something you can work with, like parameters in the light or material called luminance, illuminance, etc., that are needed for simulation, or that are the inputs you will get from a supplier like Osram, etc. That's what we understand, and it basically switches the UI that you can type in meaningful values. VRED comes with a couple of light types you can use. We have area light. No, we have point lights, we have spotlights, we have area lights, we have sphere lights, etc. Just one thing: all those point and directional lights or spotlights, try to avoid that when using ray tracing, because the information just refers to one point, which does not really exist in reality. Even the sun is an object that has a volume. It is far away, so it appears like a point, but it isn't. And in reality, it's the same. When doing light simulation or using ray tracing, try to use area lights, because every object, no matter if it's a filament or an LED, they have an area, right? And the ray tracer must trace against that. You can do, but no guarantee on realism or correctness there. But yeah, those light types, like the spotlight, for example, or the point light, come with some other features. You can also use IES files if you want. That's something you see here in the image. That's a kind of a pre-simulation or pre-drawing of how a light can distribute from the source. So it's kind of capturing how the light that distributes after the class, so not from the light source itself, but after the class into the scene. But it all, again, refers back to one point. We also have, as I said, area lights. We have also ray files, maybe something you heard about it already. It's also another format that can be pre-simulated and stored in a map, basically, or an array, let's say. And this is something we see here. So a very similar example, like the other ring light guide, but a bit differently. And those lines you see is actually the information that is stored into a light file. So the simulation was done very similar. So there is a LED light underneath, then it goes into that optical element and is separated to the left and to the right. And the information, when that light leaves the object, so the class element, is stored then inside a ray file. So it really stores the information for an object there. So what I wanted to say when doing light information, often I get asked, where do I get the information from? And I said, hey, from the supplier, so go to Osram. And people try to use those ray files or IES files for their input source, the LED itself, and then try to do the simulation for the rest of the lamp. That's not very helpful because it really just stores information, or in that case here, what you see, the photon map for the LED, but that's not what we are interested in. We are interested in how it looks like when the light emitted from the LED leaves the outer glass of the lamp. So not useful at all to use that ray file. What is really needed when you go to a supplier page is, of course, the intensity of an object. So if you go to Osram, download an LED, which lumen value that LED has. The geometry might be interesting if you do not have it already in your CAD data, just a placeholder, because it's important to have the area it is emitting light, and LEDs have different areas where the light leaves the LED itself. So you can't simply place a sphere in there and then say, yeah, you are now my LED there. You should have the right geometry, so you have the right area it is emitting light into the scene. And the color temperature or slash the color spectrum is interesting for that. Of course, you can work also in the RGB space, but of course it is more helpful to have the right spectrum, because as I said in the beginning, the wavelengths are important. So which wavelengths hits another wavelength or goes through another object that has a different wavelength might impact your end result that is leaving the object or hitting your eye. So those are the two interesting or three interesting parts: the spectrum, the intensity, and the geometry if you don't have it, or at least the size, the area of the emitting object. It is also possible, that comes in quite in handy, and I mentioned that in the beginning a bit. We also can give or make a material as an emitting light source, basically. There's an incandescence tab in the material, and when you switch that to photometric parameter, you can then also type in values, which are, because it's a material and then assigned to an object, in lumen or candela per square meter. That's again where it becomes interesting which size your emitting object has later, the LED example, but it is possible. And there are some tricks I will maybe show later, how to convert a value you get, like lumen, into a value you need when using an emitting material where you need maybe candela per square meter or lumen per square meter. But what I wanted to say, it is a nice workflow that you can do that, because if you have multiple LEDs or hundreds of thousands, you don't want to place a light over there. You simply want to assign a material and make it behave like a light. So if you once manage the conversion from that value to a material incandescence this property, you can create basically a library in your asset manager. I mean, how many LEDs does your company have? You can create a library and then simply assign it to the geometry, and ideally they are already referenced, but it's a way faster workflow to do it this way instead of placing hundreds of lights inside a tail or a headlamp. Just want to mention that. Let's talk about materials next. So materials are very important. And VRED offers a few capabilities to do with it already. Glass materials, for example, you can set a dispersion, you can have then spectral effects, basically, when you look at the caustics, like the Pink Floyd example I showed in the very beginning, Dark Side of the Moon. We have parameters like subsurface scattering, surface roughness, all those kind of things in our VRED materials. In addition, we also support external materials like MDL, Material X Substance, and those kind of things. And what is interesting is because the material topic is, as I said, the light, you can get information from the supplier, right? Which intensity, etc. But material often, especially if you try to do it with the VRED materials, there's a lot of artistic interpretation. Of course, you can measure materials with different devices as well, but it's still often not clear how to translate those measurements or values, separate measurements on the roughness or whatever, into a VRED material. So there's still some artistic, possibilities of failures, artistic failures actually possible. And that's why we introduced last year the support of translucent AXF materials, because we think that's a pretty nice solution. AXF can store the spectrum of a material. It can store the, I think they call it inner roughness, so what happens inside the volume itself, the scatter itself, but also the outer roughness, so the surface roughness, etc. The spectrum I mentioned already. So I think that's a really nice approach for a topic that has some artistic interpretation right now when working in light simulation. And with that, we started a kind of technical partnership together with an industry leader in those kind of materials and plastics, which is Covestro, to drive the format a little bit further. And please welcome Tobias Rausch from Covestro to talk a little bit about Covestro itself and the offerings. Hi.
Thank you, Pascal, for having me. I'm super excited to show a little bit what we do as a chemical company here.
Yeah, maybe I take that part quickly before you go into your presentation. So that's the part that is currently. That's why we show the safe harbor. What we are planning is that we work together with Covestro, first of all, and what we are planning is that we ship a couple of those translucent AXF materials with the application. So users that don't have a Tech 7 or just want to get in touch with what is possible with measurements in the light simulation with VRED, or basically with our application. So it works like in any other download in our library. You download it. Ideally, you move it over into the asset manager, but you can also simply load it from disk and then use it in the application and assign it to the material. So let's just wait a second and then. Right, they are in your library. All of them I have downloaded from our library, and then you can start assigning those materials. And what we do in addition this year, and will probably release in one of the next possible releases we are working on. We are working together with Covestro to allow access to their library. So you can use our web shop systems where you can also download HDRs, but you will get access to the Covestro library, where you can search for certain material looking for and download them from there. It basically works like all the other web shops we have with Substance, etc. So Toby, sorry for that, but I forgot that I want to introduce that. The stage is yours.
Oh, good. Thank you, Pascal. So, introducing Imago, this is our virtual library Pascal just introduced. Covestro, I don't know if you know us, we are a chemical company, so we're producing actually the polymers that are ending up in headlamps, in trim parts. So roughly a car usually has something between 15 and 30 kilograms of our material in different parts, and headlamps just being one of them. We're based in Leverkusen in Germany, so we're just 10 years old, but we're originating from Bayer material science, so we go back over 100 years, and polycarbonate and polyurethane are the two polymers that have been invented in our company, and we're still one of the largest producers of these materials. The problem with those materials, or especially with polycarbonate, when the material is produced, it's looking like this on the bottom here. So it's pellets, so it's very far away from a headlamp, and this makes it extremely difficult for you as designers because this material is very, very far away from the product. So even if you put it into a step chip like the one you see above there, it's still not the headlamp that you have in mind. And seeing all the optical effects that Pascal has in mind. So the only way out of this is really making them digital and starting to simulate them in VRED, for instance. So this is really helping us and to make the material more accessible for you, and also that you can experience it a little bit better with the material and create these photorealistic virtual prototypes and to see what you can get out of that material. Polycarbonate itself, it's an extremely versatile material. It can be transparent, as you just saw, but it can also be opaque. You can add this kind of speckle effect. You saw that in a couple of cars today. But there's also like changing surfaces, so you can add a surface structure to it, so any kind of texture. And there's also properties which are outside of the visible spectrum. So sometimes we have to be transparent for our LiDAR sensors, or we have to be opaque for them, and all sorts of other sensors. So there's a whole variety of things we can cover with this material. So making it digital is really very helpful, but until so far, our world was looking like this. So this is a color and design center that we're operating. And as you can see, we've created over the years lots of these material samples. So it's 10,000s of these material chips that we've created, and they're sitting in these racks. So not very accessible for you. Of course, you're always invited to come and join us, but we really want to bring that to your desk. And this is how we are going to do that. Yeah, we have all these kind of chips, so you just see a couple of those chips from a weekly production. And what we do in the real world is we want to evaluate them. And one thing you can already see with these materials, it's depending on the thickness, the color will look very differently. And also what Pascal just showed with the headlamp, it's like there is these kind of different views. So you can see it's like there is this kind of reflection. You can see through the material. And this is all these kind of effects we have to bring into a digital material twin and actually bring that into the VRED world. And this is how we do it. It's like we have these total appearance capture scanners from X-Rite. So this is a Tech 7. And you place the material inside of these scanners. And we're shooting light from all different directions on the material sample. So we learn how the material interacts with light. And that information then is stored in an AXF file. And as you can see, this is the material now in our Imago library. And you can see the rendering exactly mimics what the real material does. And that's, sounds easy, but it is quite difficult. And we make that available now in our material libraries. So we have created 2 of them. They're called Imago. And there's 2 libraries of them. There's one which is the Imago Color Finder. That's a product which we're launching shortly, as we already mentioned. The Imago Color Finder is a little bit more for designers. It's a little bit more visual. And there's the optical material data. This is more for the optical engineer. It's a little bit more technical, where you can see all the different curves, where you can start and search for specific needs that you might need for your headlamp design. Pascal.
Great.
Left you some time to show the real stuff.
Thank you, thank you. I just lost the internet connection a while ago, but let's see if it still works. Otherwise, I have downloaded some of the materials. So what I wanted to show is a bit how we can set up such a simulation from scratch and then apply some materials afterwards to that simulation. So that's again that example, right? An OpenGL, you can see it quite good, hopefully. Yeah, here's the mesh. And we have these 3 different versions to it, right? So the one that we are interested in. And when I turn on ray tracing, I do that all in GPU ray tracing by now. I see nothing. So, of course, because there is no light in here. So let's hide that light guy and bring in some light. So that's what I'm talking about is, I think, important. That piece of geometry. Right? It has a certain area and it's just the LED. When I click on that, I realize that, first of all, with a light, disk light, because I have the information from the supplier, which is the wavelength or the color temperature of that light and also the intensity, and it obviously is 46 lumen right now, because I switched into the photometric parameters already. What is nice with those disk lights is if I actually, so I really placed it there. So what is really nice, if I change the size of a disk light, you can see that also the value is changing here, because of course the area light knows about is surface, is size basically, right? So if I have a bigger light source but the same lumen, of course, it changes the behavior completely. More light, but less, or same intensity, but bigger size. And what is pretty cool in that, because my material, if I create a new material, a plastic one, that's how I would start. We don't need diffuse, we don't need glossy, we just need the incandescence over here. You can see that you have to type in a value called candela per square meter. And now that my area light has the correct size, if you simply switch in the area light to candela per square meter, you get the value the material would have. So you can simply actually copy that. I'm just showing that as an example to you. So you can copy that and take the value here. And then it also, what I wanted to show, I have, okay, I'm not using a spectrum right now. But you can also load in a color spectrum in here. If you switch to spectrum, you can basically load a file or load a curve. Let's do that. I mean, we have some time. Where is it in the demo? Look at this. Here we have a spectrum. I can bring in a spectrum. Now a red one. It's a different one than from the original LED. But that's the way how you get the right wavelength to that. Now I loaded it into the material and basically, I didn't apply it, sorry. But I think you understand what I wanted to say. So accept. Here we go. And now we basically, it might appear purple, but it's a red light with a certain intensity. And I could basically hide that light and assign that material to that piece of geometry and would basically get the same effect like a material. Instead, I can apply it to multiple objects. But yet stick to the light in here. So we have our light source set up already. So what happens now when I enable that light guide? It doesn't look like not much, right? But if I turn on the anti-aliasing, it starts doing something. But you can't really see it, because also I will hide for a second the environment, because now we have the light from the environment plus our light. So if I would set that in such a scenario, I think we can slowly see that there's more happening over here. So if I turn off that box, and now we are into that scenario where I talked about what is if I'm looking into the light and the light source itself. Why am I not really good in doing a fly to? Now here we go. So that's basically what happens if you look into a light source, right? The light goes in there. In that case, it is separated to the left and to the right, and then it starts reflecting on those prisms on the backside into my viewing direction, right? And this is how it basically works. And there's no caustics involved. It's just reflection of that LED at the very bottom. Of course, you have to make sure that your render settings itself are set up properly. And what does it really need is later on, maybe it is important to set that's what I said, the photometric parameters, but maybe we also want to enable the spectral ray tracing later on. The clamping might or might not be tried out, but usually you disable that, because otherwise your intensity values would be clamped at a certain point, and that's not what we want. We want to have it rendered to the very end, or not clamping at all, right? We need those intensities there. Also important is the trace depth in such a case. I can't count how often the light bounces in there, but I think if we set that back to the default to 8, I think it is, you won't see anything, right? You see that it's stopping at the 8th bounce, and that's not efficient. So currently we are limited, but I think that's a relic from the CPU ray tracer at 1024 bounces at all. Pretty sure that's not enough, but it's already enough to get those kind of optical effects in there. Later on, okay, no, let's do it like this. Okay, this is needed when looking into the light, no? And I of course can look with a different luminance tone mapper into that. And I have to say it's fantastic how incredible fast that samples. Not that on my CPU back then, when I created that example, it took hours overnight. I was doing that renderings, and nowadays with all the graphic cards and that amazing hardware, it's done in a few minutes and give me already guidance. Anyhow, so what is if I want to see how it looks like when that light starts distributing into the scene? So I give that environment a little bit of intensity back so that we can at least see the shape of it. Maybe a 0.1 helps there already. Yeah, okay. So if I want to see the caustic, so the light that distributes from that ring, it is super noisy, right? And if I simply wait long enough, I might get an idea that there are some caustics on the ground happening. But exactly for that case now, we have our photon mapping. So if I go into the photon mapper, into the render settings and turn on in photon tracing the caustics and indirects, we immediately see something, right? That's what I said. Those are caustics. That is the light that is emitted into the scene. And this has different other values that can impact the thing. Important is now, if you do that also you can see under the photon mapping, there's a trace depth. That's, I think it's 32 by default or something like that. Yeah, might be okay, but just to make it a bit slower and more accurate. Also, you can set that value to 1024. So it is definitely makes a difference, really depending on your geometry itself. And to show the Covestro impact, because that's what is now the critical one, I just built a diffuser at the back, so maybe we can have a look at that. So because that's what's in reality. So let's see it like this. Right, there's now something on the back that helps me to emit light to the front. So sometimes the day drive, or usually the day drive light is a scenario like that, because you don't want to go with the light backwards. You want to have it all to the front. And then there comes something into play, which most of the lamps have as well. We have seen that on that taillight example, which is a diffuser in front of that. And I think I just assigned a red material here, but if we look long enough at that, we see an effect very similar to what we have seen when looking at the taillight, but as an artificial example here. So, and this is now the tricky part, and where those Covestro materials can help, because I have zero information about what that red plastic polycarbonate, right? okay? I'm really not the expert in materials. What is the spectrum of that material? How much of that light scatters inside the inside the material, inside the geometry? What roughness has that? Is there some glossy reflection on it? I have zero clue about that. It's all artistic interpretation. So that's where that comes in handy. And I quickly want to show you something because I have downloaded the Macrolon already. It's a clear, transparent, glossy one. If I assign that simply to my shape, that's the clear one. But I think I have also. I thought I have the, okay, then I simply download it, or I simply grab it from my asset. Because what I wanted to show is more a Macrolon, a very scatter-heavy material. I thankfully have downloaded them already. Here we go. They're in here. Those are actually the ones we will ship with the application one day. And there's something in it here, the transparent frosted. Material that is heavily used for those lamps. And if I now turn on my simulation, right, we get a very diffuse appearance of the material. And this is actually a great help to get our light simulations a little bit more accurate in the future. So I think that's from my side. We are on time, a bit over. Hope you enjoyed it. And enjoy the rest of AIF then. Thank you. Thank you, both of you.